All right, let's go.
Hello everyone. Today I'll be presenting our analysis on estimating discriminability bias through positive rate and false positive rate using Markov chain Monte Carlo methods. This study revolves around signal detection theory, which helps us understand balance between signal and noise in decision-making processes. We actually explored three cases with different data sets. So to estimate these parameters and to quantify the uncertainty of our results using Bayesian framework. So let's get into the project and understand how these concepts are applied in our practice. Coming to the theoretical part, signal detection theory provides foundation for understanding how we distinguish between signal and noise in making decision processes. It introduces four particular key parameters. One is discriminability, bias, true positive rate, false positive rate. Discriminability, it represents how well the signal can be separated from the noise. So higher the discriminability indicates clearer distinction. Coming to the bias, this reflects the decision between threshold or criterion, which indicates whether system is favoring detecting signals or is it avoiding false positives. Coming to true positive rate, it's the proportion of correctly identifying the signals, and false positive rate, it is the proportion of noise trails that were mistakenly classified as the signals. So from the study, we used a Bayesian framework, which is a Markov chain Monte Carlo method to estimate the parameters. Then we leveraged the no U-turn sampler nuts, a variant of Hamiltonian Monte Carlo, to efficiently sample from the posterior distribution. The priors were defined for discriminability and bias, and TPR and FPR were calculated using the resulting estimates. So here, from now, my friend will continue.
All right, thanks. Thanks, Gurram. So we the results that were achieved, we can see that in case one, we have an average of 0.52 for discriminability, average of negative 0.26 for bias, and negative and 0.7 for TPR, 0.5 for FPR. And this, based on these results for case one, this tells us that we have a moderate ability to distinguish signal from noise, um, and um, and that we have a very a liberal bias. This means that the this means that we won't find we won't be able to easily, or rather a negative bias means we're gonna have a high false positive rates. In case two, we have very similar uh, parameter estimates as case one, but but with greater uncertainty due to smaller data sets. We see that the liberal bias persists, leading to high FPR, and we have a wider uncertainty interval because of limited data. As you can see in the HDI, like basically, what this means is that we have a high range difference. In case three, we had a very ideal case where we can, because we have a very high value discriminability, we can easily separate signal and noise. I'm going to pass it on to Sravanthi to conclude. Sravanthi? Kadari?
Yeah.
Go ahead.
So the conclusion I'll highlight are key findings of using a Bayesian framework. The analysis used a Bayesian framework to estimate important metrics and quantify the uncertainty of these estimates. Bayesian methods are advantageous because they incorporate prior knowledge and provide probability distribution for parameter. This approach is useful for small data set. Our key project takeaway is that the project demonstrated how combining SDT with Bayesian inference can give a more detailed and nuanced view of a statistical decision. This combination allows for a deeper understanding of trade-offs in statistical tests such as balancing sensitivity and specificity. Our future direction would focus on optimizing the decision threshold or criteria to reduce false alarms and maintain a reasonable level of sensitivity. Thank you.